So we can capture all of that in this generalized definition of what we call exigence. And then, of course, you have your normal radiosity component that is coming in because of some external source. So there are two values that actually provide for the full radiosity of an object. Okay. And the general idea is that you can model all of that in some additive form, an exigence form, and in general the radiosity due to the incoming radius. So what aspects of it do we truly try to model? Right? Because there are so many things that affect the energy emitted from an object. Well, so we can try to define radiosity that is due to a point source, first and foremost, right? We can just assume that the illumination source is very, very far. As a result, it's going to provide an energy that is defined within some narrow cone of light and become a point source at some point. So we can compute that, and in general, that can be approximated by the factor of pi multiplied by epsilon divided by d, as long as the distance to the light source is far greater than actually the area on which it is illuminated. So we can approximate that through that term. And if we do that, then of course the radiance patch due to that particular source is going to be just a point on the surface. So, well, okay, we can try to model that. We can assume all the light sources are very far. And if we do that, then what happens? Our radiosity will become pi times L naught, right? And L naught, we can express that in terms of the albedo component of the object, integrated over the irradiance function that we have. Okay, so that is L cos theta I. And of course, we are integrating over the area. So we can simplify all of that, and that again will be expressed eventually in terms of nothing but things that we have seen in the past, which is my albedo times cos of theta I. Now, of course, we have this modulating factor, which is the distance of the source. So divided by r squared. And we have seen this before, which is as we go further away from the object, the amount of energy that we capture falls off with respect to the distance. Right? Okay, so that's for something that's very far. What if something's kind of nearby? What happens when the source is nearby? Well, the only difference that happens when the source is nearby is that now I have to actually account for the actual magnitude of the source. When the source is very far away, the magnitude is almost gone because it's uniformized across the entire object. We integrate it over the entire source. But when the source is very narrow, you're going to have a much more directional energy coming in, so I will account for the magnitude. So if you look at this, the formulation is more or less the same, right? So you have n dot product with the source vector. So this will add, if I had to say the magnitude is defined by some value k, then this becomes rho times k cos theta divided by r squared, as opposed to when the source is very far away, it's nothing but rho times cos theta divided by r squared. That's really the only difference that happens when we look at sources that are much closer to our object rather than things being very far. Okay? Everyone okay with that? So the standard distant point source then in reality that we end up using more commonly for calculational purposes is something where we just use our standard diffusion model. We assume that all the points in the models are close to each other with respect to the distant source, and then the source vector is not going to vary much. So if it's the same source vector everywhere, then what's the difference? Everything just modulates up and down. Nothing actually changes on a point-wise basis.
Another thing could be multiple points in the object could be illuminated, or just one?
No, multiple points. Absolutely, yes. Multiple points getting illuminated. So all we do is take all the constant values that we have and roll it together, right? So remember, all of this relates to L, right? And L has some relationship with intensity. But if we roll all the constants together, all you're doing is modulating L. It won't affect anything in terms of the relationship between intensity and L. Now, we know that obviously, depending on the light source, certain objects will cast shadows. So if I have interaction with multiple objects, some objects may cast shadows on other objects. Right? And this distorts our entire view of what a point source model may explain for us. So, for a point source, of course, the geometry is simple. But how do we handle other sources of illumination that may not be expressed as point sources? So nearby objects we know we cannot express as point sources. Distant sources of light, great, no problem. Right? But shadows are not typically something that we account for based on distant light sources. Shadows we have to actually explain in terms of sources of light that are close to us. Because they are the ones that will cast large shadows. Things that are far away don't matter much. Okay? So, when we want to do that, we have to start thinking of area sources as opposed to point sources. So what that means is that if I have, let's say, a source, right, which is non-point source now, so it means it's some kind of planar source, simplified area source. It will probably emit a certain amount of light in a particular direction. And a portion of it is going to go onto my object. The question is, what portion of it will go on that object? We know that the light actually, under all our models, we always modeled it as being something that's directional. So I can express the same thing in terms of the surface. If I know the normal of the surface, then there is a particular direction in which this source will illuminate my object. But since it's an area object, not a point object, I can't simply model it as my little cone or my solid angles appended. I have to model it in terms of my area. Right? So we simply extend this to an area model and we change our variables around a little bit. Okay? And you can sort of follow through the math if you like. We can run through this, but it basically is exactly the same model that we looked at for the subtended angular direction of illumination, except now we're going to change some parameters around and compute the area. So rather than having everything expressed in terms of pi multiplied by the distance or the angular direction divided by the distance, right? We have to account for the energy per unit area, right, divided by pi. So I will try to still capture that in terms of my energy. And then, of course, you have cos of theta I, which is the normal it makes with respect to the area source. But then you also have the amount of area that is to be expressed with respect to the normal of the object on which the light is emitted. So all of that will then eventually integrate into this term. So you have cos of theta I, cos of theta S. So those define the angles between the area source and my object that's getting illuminated. And you still have a normalizing factor, which is defined as pi r times r being this function that's actually the function of the area. Okay. Now these are useful when we start looking at shadowing effects. So this is what really causes shading, right, in our observations. So where do we get shadows from? Where do we get shading from? Shading is nothing but self-shadowing or some other object shadowing something else, right? Otherwise, if things are always uniform, then everything will always be uniform. So shading models are really come in two flavors. You can have local shading models and you can have global shading models. Local shading models basically say that, well, the surface has a radiosity due to sources that are visible at each point. Right? So I compute for every point in my object and solve the equation that we looked at. Right? The relationship between some source, my geometry at that point, and what the camera is, or the viewing angle of the camera. solve for everything on a point-by-point basis. So that's really my local model. So the advantage of that is, well, it's easy to manipulate, right? Because I'm truly only dealing with a point value. I don't have to look at my entire object in its global structure. I only have to worry about the normal at a local point of the object.